welcome back. So we are starting a new unit on galaxies and cosmology in the 21st century. And so you want to make sure you get a hold of your new study guide that will have all the bullets of the new chapters that we're going to be covering in this new unit. Before you begin, make sure you have that. Use your resources such as the PowerPoints, your textbook, and that all-important study guide. So with our new unit, so we are continuing to branch out in the universe. We finished our star unit, we took a look at the sun, and then we looked at the family of stars, and now we're branching out to our parent galaxy, the Milky Way galaxy, and then we'll continue to branch out further and take a look at the classification of galaxies as a whole in the universe. And so our what are we summary for this chapter, chapter 12 is where we'll begin, is that we are children of the Milky Way. Which is very fitting because in our last chapter, chapter 11, it said that we are stardust. We are created from the dust of these dying stars, supernova explosions, sort of thing, and that this is our parent galaxy, and so we are created by the Milky Way galaxy. It's very fitting extension here. And so we do want to get started. We'll take a look at some of the properties of the galaxy, how we even realized that we were inside of a galaxy. That's a rather new kind of concept within the last 100 or so years. We didn't even realize that we were inside of a galaxy. If you remember the ancient astronomy chapter where they thought our little bit of solar system was the universe, and so we're actually inside of a galaxy universe full of galaxies. So chapter 12 is where we're beginning. We take a look at the Milky Way galaxy first. The Stars Are Yours, a title of a popular astronomy book written by James Pickering in 1948. That's, the title, the point of it is that the stars belong to everyone equally. We can all enjoy it just by taking a look up and out in the night sky as if we owned it ourselves. And so we actually do live inside of one of the largest star systems that fill the universe. A little statistic there that our Milky Way is over 80,000 light years in diameter and contains over 100 billion stars. And so it's tremendous, but yet it's still only one of billions of galaxies out there. And so we learned kind of last time that stars, atoms heavier than helium get cooked up in our very massive stars. If you remember that, up to iron. Iron was kind of the end of the road for our stars, and that they would go through a very rapid death after they reach that point. And so, yes, how the stars of a galaxy are kind of ones that cook up these heavier elements, and then during the supernova explosion, where temperatures are so high that finally we can get even iron to start to fuse and react, and then that creates even heavier elements during those supernova explosions. So kind of element building cycle will be talked about in here. So this PowerPoint's kind of reiterating that and how the stars in the Milky Way have generation after generation made up the atoms in our body. And so we are created by the Milky Way galaxy, and we are stardust. And so very fitting for our new unit here, the what are we kind of summary in there. Okay, so we discovered something that's all around us. It might seem odd that yes, this galaxy is all around us, but until about the 20th century, no one knew that we were actually inside of this galaxy, what that Milky Way even was. And it's really not obvious that we are inside of a galaxy. We see, some nearby stars kind of scattered all around, where the more distant ones are actually hidden because of all the gas and dust. We can't actually see it, but it does appear to be like a cloud, kind of a faint band circling the sky. The Milky Way along there, sort of a cloud, Milky Circle, they call that. The Greeks from there. The Romans kind of call it Via Lactea, so Milky Road. So various things, but eventually we concluded that Milky Way was a good name for that. And so it really wasn't understood that we were inside this great wheel of stars known as our galaxy. So they called those galaxies. Galileo's telescope revealed sort of that band, the glowing Milky Way, lots of stars in that. But this idea that it was more wheel-shaped, that took a little investigating. For that, we have a couple, an astronomer here, William Herschel, and his sister Caroline Herschel, where they were trying to gauge the actual shape of the galaxy. And they just did this by counting a lot of stars here in 683 directions. They started counting across the sky and trying to gauge this. Where they saw more stars, they assumed that, you know, the star system extended a little further into space. And so they came up with a little picture where, you know, it kind of looked like, oh, there was a few little gaps here and there, but sort of this disc kind of look shape to it, with maybe the sun and the earth being somewhat towards the center, which, you know, if you're looking out from the earth, it may appear that you're the center. We later find out that no, we're not at the center of our Milky Way galaxy. So that was sort of the beginning of it, that the center of kind of a wheel of stars. But the real truth, how we kind of realize the truth about the size of the galaxy, Earth's location within it, that we were actually in a very large galaxy, and then later on that there are many galaxies out there, not just ours. So this sort of adventure they talk about, it begins with a woman studying stars that pulsate, and leads to a man that studied these star clusters. And so we've got a couple people we're going to introduce to you, how scientists sort of build on the work of their predecessors. And we saw that when we looked at the ancient astronomers, how, you know, the work of Kepler and Galileo, and it kind of all got handed off to Newton, who took it a little further. And so this is sort of that step-by-step trying to make sense out of the natural world here. Okay. Let's see. Yeah, so it's a common misconception that the stars are eternal and unchanging, as we certainly found out in the last unit on our stars, that stars are born, right? New nova and such make their appearance, supernova explosions, so stars do die. Yeah, so they get brighter and then they fade. So what was happening was they were able to actually, a woman named Henrietta Leavitt, that there were some variable stars that kind of pulsated, meaning that their brightness would become intense and then it would fade and go back kind of in a cycle, in a period of this luminosity. And so we're going to look at and they're called variable stars. So we're going to look at some types of variable stars that allowed astronomers to actually get the size of the galaxy to very influential people. And so in 1912, Henrietta Leavitt, another woman astronomer, she was studying a cloud, a star cloud in the southern sky known as the Small Magellanic Cloud, right here. So she was taking some pictures, and she was just actually looking at the photographic plates and noticing their brightness, so their diameters on the photographic plates would get a little bit larger and then a little bit smaller over time. So these pulsating stars is what she would call them. These variable stars, she noticed that the brightest stars have the longest period. So it took the longest time for them to go to their peak brightness, and fade, and then back up to their peak brightness. So their pulsation period, she would call that. So your most massive stars are your most luminous, right? The brightest ones. They have the longest pulsation periods. So all the variables were in the same cloud, and so therefore at nearly the same distance. And so this becomes sort of a marker for distance. Remember our extragalactic distance ladder. This is going to be like the next rung up on our distance ladder, being able to use these variable, Cepheid variable stars, they called them. So yeah, and so we could end up using then, she figured out, that there was a relationship between that pulsation period with their luminosities, their true total power output of those variable stars, okay? And of course, we had another gentleman who figured out the distance part of that. So the stars that Henrietta Leavitt saw, we now call them Cepheid variable stars, okay? And they're named after the first such stars discovered in the constellation of Cepheid. Okay, and so that's why we kind of get the name for it, Delta Cephei. And this is a light curve, and so again, across the bottom here, time, so the period, right, in days. And then on the axis here, we're getting visual magnitude, so apparent visual magnitude, her apparent brightness in there, and going from its brightest peak, and then it dims back to its brightest peak again. And so how many days had passed during that period? Okay, so pulsation period is what she was being able to come up with for these stars, these variable stars, she called them, pulsation periods in there. And so what we were coming to realize is what was happening because they were pulsing like that is that they were actually in this, what we call the instability strip. So the stars were kind of evolving and kind of going through changes internally in their star structure where they're going off the main sequence a bit, right? In this instability kind of strip where that was changing their luminosity a little bit and their temperature a little bit. So the internal workings of the stars beginning to kind of go in those giant stages where they're evolving off of the main sequence and, you know, beginning to slowly go towards their deaths, of course, but changing luminosity and temperatures, which would cause them to what they kind of pulsed, is what she was seeing. So as they're going through that instability strip, they are starting to pulsate. And they stop pulsating when they evolve out of that strip. Okay, and so that's sort of what was happening internally, some different things going on with our stars. So here we have a relationship where the more massive stars, of course, they're larger, they are more luminous, right? But they also have the longest pulsating periods. So the larger, more massive ones were more luminous, but they pulsated slower. The smaller ones were less luminous, but yet they have a longer pulsation period with them. So there was sort of this mass luminosity kind of relationship happening as well. So lower mass stars were less luminous. Being smaller, they pulsated faster. And so the long period Cepheids are more luminous than the short period Cepheids, and she was really able to see those longer period ones because they were more luminous. It was easier to kind of see, but that was period luminosity relationship that we did look at before, how the luminosity and related to their luminous, how large they were, massive, and luminosity relationship. But now she's related it to this pulsation period as well. So period luminosity relation. And so she's got a little table here of some absolute magnitude or luminosity and the periods of days that they're pulsating, and several types in here. She did first start out with the delta Cepheid variable stars, but then they've kind of separated them into type 1 or the classical Cepheids and type 2 Cepheids, and they've even found some Lyra in the constellation of Lyra in there. So they're learning about more and more of these as we go. So she was trying to get, you know, absolute magnitude with these periods of luminosity. So she was the first to kind of notice these. And then comes along, who knew about Henrietta Leavitt's work, but a young astronomer named Harlow Shapley, 1885 to 1972 is his time frame. And he really began to understand the true nature of the Milky Way. He was really very interested in the distribution of stars in the Milky Way galaxy. And he was noticing different kinds of star clusters have different distributions in the sky. Now we have looked at, we briefly mentioned, and I mentioned that, when we get to galaxies, we'll talk a little more about it. But the open clusters, okay, and globular clusters. And so the open clusters, remember, they only had, 100 to 1,000 maybe stars in them. So a little bit younger stars, that sort of thing, concentrated. And then the globular clusters, those very densely packed stars, and 100 billion kind of stars packed in a small space, and that those had maybe the older type stars in them. So he figured out, there's this difference in kind of the distribution between these star clusters. So open clusters are concentrated along the Milky Way. Globular clusters kind of scattered. Widely scattered. So he kind of honed in on the globular clusters for this, but he was noticing that the globular clusters were more common toward the constellations of Sagittarius. So meaning that direction on the sky, not that it was the stars of Sagittarius, no, but in that direction on the sky. So toward Sagittarius, he was noticing that there was a lot more of these globular clusters concentrated in that region. And so he was coming to kind of the conclusion then that the center of the galaxy is probably off toward that direction on the sky, off towards Sagittarius constellation. Not in the constellation, but toward that way on the sky. So that this is sort of the combined gravitational field of a star system, kind of congregating things around that center of the galaxy. So his work was very influential. And he could study the size and the extent of the galaxy by studying that distribution of those globular clusters. And of course, we needed that ever important measurement of distance, okay, to as many globular clusters as he could possibly find. Well, these were very far distances, much too far away to get the measurable parallaxes, right? Because it's such a small angle the farther you go out. And so he knew about Henrietta Leavitt's work with her Cepheid variable stars. And so he was able to kind of look at those ones that are, the very bright stars. So they're almost like a beacon out there, easier to see. And that he could set up a distance relationship between those Cepheid variable stars. And so he knew about her work on that. And he was going to kind of calibrate her work. Her work depended on the relative luminosity rather than the true luminosities. And so if he could get it calibrated for the true luminosities, we already have a relationship. Let me pop that under there real quick on how he could come up with the distances of these. Switch to the camera. I believe I've put this under here before. Okay, let's see if I can zoom maybe a little bit. So if you have, where you could take a photographic plate and find just their apparent brightness, how bright a star was visually, okay. and get the absolute visual magnitude or the luminosity, so that intrinsic brightness from that, you could then calculate the distance in there. And so that is pretty much what he was doing, determining the distance to globular clusters using the Cepheid variable stars. So he was able to do that. Let me maybe write that on the board for you, this relationship. Not that you'll be calculating any of these, but taking, you know, say if you had any of these two here, okay, you could come up with, as a lowercase b for apparent visual magnitude, the capital M sub b for absolute visual magnitude, or luminosity could be substituted in there. And you've got that over the distance squared. And so he could actually calibrate this relationship to get at the distance. That is actually our next rung on our ladder, our extragalactic distance ladder. Put that back up under here. Okay, so if any of the two of these three quantities are known, the other one can be calculated. And so, see how well we can see that on here. Not real sure how that's showing up for you, but we've kind of made our way up our extragalactic distance ladder. Last time we looked at the spectroscopic parallax with the spectral classes. Remember that? O, B, A, F, G, K, M, our spectral classes, right? Could use that. Now we're using those variable stars, the Cepheid variable stars that Henrietta Leavitt used, and you're seeing, you know, going to a peak brightness, dimming, going back up to a peak brightness, so able to get a period luminosity relationship from the work that Henrietta Leavitt did. So that's actually our next rung on the ladder, and these would be good for distances. Now we're starting to talk about distances between galaxies, so 10,000 parsecs to about 25 megaparsecs. And so we're starting to get much and much greater distances. And of course, all of these distances, the interesting thing about it is they do depend on the lower rungs, how well your information from your lower rungs on the ladder are as we build with our distances. And so that is the method that gets used for the next rung there on our ladder of using those variable stars. And that's what Harlow Shapley did. He actually used those Cepheid variable stars and determined where the center of the galaxy was by plotting the distribution of those globular clusters and figuring out the distances between them. So he had a nice method there to come up with that. Okay, so yeah, he kind of calibrated for the true luminosities in there. And so statistically, he was looking at sort of the processes involving measurements of the position shifts due to motions through space called the proper motion, so looking at the stars. And he was able to find the average distances of a few of those nearest Cepheid variable stars, those beacons out there. And he found their average luminosities. And so it's said that he has calibrated this for variable stars to determine distance using that. So that method in there. So our next rung on the ladder there, variable stars, can be used to determine distance. And that's kind of what he did. So he was able to replace Leavitt's apparent magnitudes, right, with the luminosity, okay, from the luminosity period diagram relationship. And so he ended up calibrating the variable stars for distance determination. So kind of using someone else's work and building on it. That's what scientists do, okay? That's the hope, to take it a little bit further. So having calibrated the Cepheids, he could find that distance to the globular clusters. And he plotted the direction and the distance to many of those globular clusters, and he found that they formed a great swarm that's not centered on the sun, like the Herschel's duo, brother and sister duo, thought it was all kind of centered around the sun, which kind of it would look that way if you were just kind of looking out from the Earth like that. But he found that they form a great swarm, but that is not centered on the sun. So kind of finding the true location of the sun within our galaxy. We're not in the center of it. So here was where the center of those globular cluster clouds were found, right about through here. And the sun was some distance away from it. So we're kind of out there in the suburbs of our galaxy in there. So the center was in Sagittarius, in the direction on the sky of Sagittarius, the constellation, and it was very far away. So the star system, we were coming to the realization that it was much bigger than we had first even realized. So Harlow Shapley did us a great service just in understanding kind of where we were within our own galaxy there. So it was much larger than we had originally thought of it. So we don't live at the center of a small system, but we kind of live out on towards the outskirts of this big wheel of stars, a galaxy. So, and why did we think before Shapley that we were near the center? And again, a lot of the gas and dust out there is kind of obscuring our view, and so we couldn't really see. All we could really see was this sort of band of Milky Way, which is kind of in our neighborhood of the sun, and so the rest of it was kind of blocked out from our view, our visual wavelengths anyway. And so in order to kind of study the galaxy, we need to use different wavelengths, more longer wavelengths, dust penetrating wavelengths like the infrared wavelength or even radio wavelengths. And so yes, there have been studies with this. So yeah, so outside the Milky Way, not blocked by too much interstellar dust, and we of course could see that. But in 1923, Edwin Hubble photographed actually individual stars in the Andromeda galaxy, so sort of a neighbor of ours, the Andromeda galaxy. And he was able to find some Cepheid variables there in 1924, which of course allowed him to estimate their distances, right, and get those distances calculated. And it became clear that our galaxy was just one of billions galaxies out there, just a universe filled with galaxies. And so again, that was, 1923, 1924, not even quite 100 years ago when we finally came to the realization that, yeah, we're in a galaxy and we're just one galaxy out of a universe filled of galaxies. So barely 100 years ago, and we're just coming to this realization. Okay, next we want to look at the analysis of a galaxy, kind of the components, parts of a galaxy. Two basic primary components, a disk and a sphere, okay, kind of component. And the disk component, so here's kind of a top view and here's kind of a side view that they're showing us. So the disk kind of flattened portion of our galaxy is what includes those beautiful, in our Milky Way galaxy, a spiral galaxy, so the spiral arms, sort of in that flattened disk region. And then there is also a spherical kind of component that includes that central bulge out in the middle and a halo. So a much more kind of least densely populated halo out there. There's lots of globular clusters out there in that halo. Okay, so the disk component and then that spherical component that's composed of two things, the central bulge and then the halo. Okay, kind of an extended halo out there. So Disk includes stars, open star clusters, so younger stars in that disk kind of portion. And nearly all the galaxy's gas and dust is within the disk component, okay? So there are great variations between the disk and the spherical component. Lots of gas and dust, and of course, we learned in our star formation that that's the site where you're going to get the new star formation. You've got to have the material that creates the dense molecular clouds to where you can get some sort of, shock wave going on that would create new star formation. So it makes good sense that we have some very brilliant, very luminous, bright, massive stars in there. So it's a star formation kind of region, illuminated by the recently formed blue, very hot stars. They're massive stars, so our giants and our supergiants. So they're going to be hot and kind of have that blue kind of hue, and so the disk does kind of have a blue hue to it from those massive and very hot stars. And so the gas and the dust kind of block the view of the plane of the galaxy. So we can't really see to the center or the edge very easily because this is where a lot of the gas and dust is. So it's not really well defined where the edge is. But then again, like I mentioned, they do try to get at it by looking at different wavelengths. But the best studies suggest that it's about 8.5 kiloparsecs now. We're putting a prefix in front of our parsec, which is 1,000 parsecs, right? So 8.5 kiloparsecs from the center is the best estimate on that. And that the sun appears to be about, you might not be able to see that, but this little arrow here, where the sun would be about, 2/3 of the way from the center out from the galaxy, and then they put the sun here as well. So not at the center, about 2/3 of the way out, and on a spiral arm, kind of 2/3 of the way from the center. And we're going to see that some strong evidence here that shows that our galaxy is actually much larger than this luminous portion, that there's an extended kind of a region that's non-luminous. So how we're going to study about that, that'll come up here in just a little bit. But making observations at various wavelengths, longer wavelengths, in infrared. So this one's called the far infrared image, and it just helps us to see through the gas and the dust. So this image here reveals a little better the disk of the galaxy there by using different wavelengths that we can get through that dust. Okay, those photons, are at a wavelength that they're unaffected by the dust. So the most striking feature of the disk component is those spiral arms. In a spiral galaxy like ours, long curves of bright stars, star clusters, gas and dust, okay, easily visible in other galaxies as well. So there are many that are spiral, but not all of them are spiral. And later how astronomers found that our own galaxy has this spiral pattern to it. Okay, so that was all the disk component. Now they're talking about the second one here. The second component is that spherical kind of component in through here. And it's got two parts to it. One I mentioned was the central bulge. Okay, so and then the halo farther out here. Okay, so matter in the galaxy scattered in sort of this spherical distribution around the center. The halo is kind of thinly scattered with some of those globular clusters, and so these contain, very little gas and dust out here. And so really this has no raw material for new star formation. So we don't get a lot of those young and bright stars out here like we see in the disk materials. Not a lot of raw material so no new star formation really occurring out here in the halo region. So those globular clusters, those older stars, tend to be out in that region. Little gas and dust out there. Okay, so as they're saying there, these are mostly the old, the cool giants, the dim, the lower main sequence stars. So there could also be a lot of older white dwarfs in there, but those are very dim and really difficult to detect. But yeah, they've kind of mapped out the galaxy by trying to study more of the giant stars that are in there, but you know, they're not like the bright, hot, luminous young stars of the disk. So there's quite a distinction between the disk region and then the spherical halo, or the central bulge, and the halo, which is the spherical component. There seems to be setting up quite a difference between those kind of components. And so here they're talking about the central bulge surrounding the center of the galaxy. Little gas and dust, as I mentioned, so little star formation in the nuclear bulge. So older, cooler stars, like we see kind of out in the halo as well. So quite a difference between disk and spherical components. You want to make a note of those differences. Okay. Getting at the mass of the galaxy, just like we wanted to get at the mass of our stars during the star unit. Well, how massive is it? Well, we needed to find the masses of stars, right? Back a couple chapters in there, and we were studying the orbital motions of the pairs of stars in binary systems. If you remember that they would orbit the common center of mass between those two stars, and we could get at their masses by looking at, well, what were their semi-major axes, right? How far were they from that center? And then what were their orbital periods as well? And so we do a similar thing to find the masses of our galaxy. We want to look at the orbital motions of the stars within the galaxy, okay? And so, yeah, a star in the galaxy is going to follow an orbit around the center of mass of the galaxy, okay? And so, similar to like what our stars were doing, but this is going around the center of the galaxy. And the disk stars tend to follow parallel circular orbits within the disk region. And so this idea that the disk of the galaxy rotates, okay? And so we can start to kind of set up a rotation, okay, that will allow us to estimate the mass of the galaxy. And so let's see. Looking at how they move, and we can also do the Doppler effect to reveal the radial velocity. So a star coming toward us, the observer, or away from us, and what is happening with this speed, the orbital speed. So the radial velocity. And so there's a couple calculations. I don't know that I necessarily need to write that all out. On the way we learned about the masses of the stars, we are extrapolating that to the mass of our galaxy as well. So we're looking at the stars' orbital periods, their distances from the center of the galaxy, and their speeds as well. So radial velocity. Combining all that information, we can find the shape of a star's orbit around the galaxy. And so there were kind of some distinctions between the disk component stars and the spherical component stars we were seeing. And so in the halo, quite strikingly different from those of the disk, as we can imagine. Here they're talking about kind of the halo stars. Their orbits were, you know, going more in a very elliptical kind of a shape, not so circular, right? So these are ellipses, and it almost just looks like a swarm of bees kind of swarming all over the place. But so more of an elliptical type of an orbit, okay, out there in the halo kind of stars, random movements and ellipses for their orbits of those stars. That's sort of the spherical component stars. In contrast, the stars of the disk were moving in nearly the same direction, so we have more of an orderly pattern here. Circular orbits, okay, in the plane of the disk, okay, nearly circular around the galaxy and stayed within the disk. So they weren't swarming in all these elliptical things like the halo stars were, more a circular, okay, orbit within those of the disk. Okay, so we could use these orbital motions to set up the masses, to find the masses of these, and that's what they did. And so was how we found the sun orbit. They were saying that it's within the disk, so our sun is within the disk portion with a radius of 8 kiloparsecs. And so we can find out that the sun has completed a single orbit in about 220 million years. It takes a long time, that's a big galaxy, to go around in its orbit. So the sun does orbit within our galaxy. Okay, so, and we are orbitally locked with our sun as it does its orbit around the galaxy. Yeah, and so you can kind of estimate this. So that's kind of what they did. Let's see, I think there's a chart coming up here. But what they were doing was looking at estimates that included the mass just inside the sun's orbit. So you remember how the sun was about 2/3 of the way out? So we were able to get the masses of all those stars within, closer in, of those stars from the sun in there. And so it kind of gave us a lower limit of the mass of the galaxy of 100 billion solar masses. But no one knows exactly how much to increase that to estimate the rest of the galaxy further out from the sun. You know, so, and here they're speaking about the measured motions of the stars that it's not rotating like a solid body, okay? There's actual differential rotation. Some of the stars have shorter or longer orbital periods than the sun, so that differential rotation, and we learned about that in the actual sun's rotation itself, how that was a little bit fastest at the equator and slower as you got to the poles, differential rotation, if you remember that. So this is what's going on with all the stars around the galaxy, that there are shorter or longer orbital periods, so that you do get sort of a differential rotation happening. Should be a term that we've heard before. But here's the graph of the orbital velocity of the star at various orbital radii throughout the galaxy, so towards the center and outward a ways, and it's called a rotation curve. So along the bottom axis here, this is the radius in kiloparsecs, and so 0 would be at the center of the galaxy, and then, you know, 2 kiloparsecs, 4 kiloparsecs, 6, 8, 10, and so on. So you're getting farther away from the center. And then along here, the orbital velocity in kilometers per second. So how fast the stars are orbiting. Okay. And you've got a red curve here. This is the actual observation of what was happening. Okay. And then trying to use a prediction, mathematically predicting what should happen. We were using the dash line here, okay, called the Keplerian motion. So Kepler's third law was talking about how orbital velocity falls at larger radius. And so if you remember, when we were talking about the motions of the planets in their orbits, as they got closer into the sun, they would speed up in their orbital periods. Speed up a bit. Then they got farther away from the sun, they would slow down. Okay, so they were trying to think, well, if it was following that Keplerian motion, if most of that mass was towards the center of the galaxy, those should have the fastest orbital speed, but the further away you got from the center of the galaxy, those orbital speeds should slow down. So see how fastest is your closest in, this would be the Keplerian motion, and slower as you got further away from the center of the galaxy. Well, that's not what they observed. They actually observed, look at it, it goes up. It actually starts to go up and kind of steadies out there. So this is the actual observed rotation curve. So they're thinking, well, what's going on here? Where your velocities are rising at larger and larger radii away from the center. So that must mean that there's actually more and more mass as you go further away from the center of the galaxy, which is an amazing thought. But we're not actually able to detect it. And so, but from this rotation curve, that prompted them to think, well, maybe there's some non-luminous matter, okay, out there, this dark matter that we talk about. So large velocities are seen at those larger distances from the center, okay, which suggests the existence of a non-luminous dark matter in what they call kind of this extended halo or this dark halo. Okay, so it really didn't follow that Keplerian motion, right? As in the case of our solar system, right? So that meant that the galaxy's mass is not all concentrated at the center. And if most of the mass is inside the orbit of the sun, well, you would expect those orbital velocities to decline at greater and greater distances, but that is not what they actually found. And so it does seem clear that large amounts of matter are located beyond what seems to be the limit of the galaxy's luminous matter, so that there's this non-luminous matter we call dark matter. So this is what prompted us to kind of think about dark matter, which we'll have more to say about dark matter in chapter 14. But yeah, that extra mass is kind of extended out in the halo, and it's sometimes called the dark halo, but maybe 10 times farther out from the edge of the visible disk, okay? And maybe upwards of 2 trillion solar masses in that there, so quite a large part there. Okay, so most of that matter is not producing light, so that's why they call it non-luminous, or that's where the term dark matter comes from. So there is some yet unknown kind of form of matter, which is a fundamental problem of astronomy. And they are starting to get a handle on the dark matter. But in our chapter 14 on cosmology in the 21st century, we will have more to say about dark matter and the evidence for it. So that's something to look forward to there. But using that kind of rotation curve there is how you can find the mass of a galaxy. And so that includes orbital velocity versus the radius in the disk of a galaxy. Okay, so the beautiful spiral arms. Most striking feature of the galaxies like the Milky Way, okay, the spiral galaxy there. And it has a lot of the bright, hot, very luminous stars, young stars, so they are young objects. And so to trace these, what our spiral tracers are for the spiral arms, you want something that's very luminous, easy to see, and very young, so that we know that these stars have pretty much been born, were birthed very near where they are located, because you remember our very massive stars, they don't live very long lives, and so they haven't really traveled very far from their birthplaces. And so we want the objects to be young, and we want them to be very luminous. So the hot O and B stars, those giants and supergiants, O and B stars, make great spiral tracers that we talk about in here. So the hot blue stars is one way to kind of study it. We can see them very easily. It's not very difficult. The O and the B stars are often found in associations. Very luminous, so they're easy to detect, as I mentioned. And at the great distances, you know, their parallaxes are very small, but we can usually use spectroscopic parallax. Remember, that is a rung on our distance ladder to get to the distances. So many methods we can get at distance for these. So the spiral tracers, definitely you want them to be very luminous, so your O and B stars, and young, so that they haven't traveled very far. So those are the spiral tracers, and they're saying, okay, here's a spiral arm, here's another one, and well, the sun's right about there. And so the O and B associations are good spiral tracers because you can see those at great distances. And young, open clusters where you can definitely see the hot kind of ionized stars, and they haven't really moved very far. So young and very luminous stars are good spiral tracers. Okay. Keeps on saying it. Young objects and very bright. Okay. So we kind of move on a little bit through there. Let's see. That these spiral arms are actually a little bit irregular. They have little fragments, they have little spurs kind of coming off of them. So many of those irregularities actually do seem to be real. And so trying to compare the available data on our galaxy's spiral pattern with what's seen, you know, in other galaxies, we want to kind of pull together a model here that maybe we have some tracers that would suggest active star formation within the spiral arm, so that this could be where our new stars are forming, and it makes good sense because that's the region in the disk that it's highly populated with gas and dust. I mean, the raw material to make our stars, that abundant in these spiral arms. So these are very active star formation regions, and it makes good sense that we're going to be finding some young stars in that location. Now they're trying to come up with a theory here about how the spiral arms may be formed, but it's called this density wave theory. It proposes that the spiral arms are waves of compression around the galaxy that just continues to perpetuate star formation, kind of a self-sustaining star formation, but density waves. And so if you remember how that gas and dust just doesn't want to condense kind of on its own, I mean, you'll get more dense regions, dense molecular clouds, but really doesn't want to collapse, and so we need some sort of a shock wave, which if you've got these very massive stars, those O and B stars that live short lives, right, because they're so massive, the deaths of those, the supernova explosions, remember how those can cause that shock wave like a traffic jam there, and allow for star formation to happen. And so that spiral density wave kind of becomes compressed, and eventually they move out kind of in front of the arm, leaving kind of the slower moving density wave behind, and you can get those little spurs and fragments to kind of happen during this. And so you know, that's some of the reason why we're seeing some of those spurs, but this little picture is just kind of showing how we've got a very dense gas cloud coming along, and that suddenly gets compressed and creates, you know, some new stars to form. I think there's another picture where it continues to kind of give you some massive stars forming. Of course, our massive stars aren't going to have moved very far away from their birthplace, right, in there. And so this is the idea of kind of how our spiral arms might be forming. Okay. Little low mass stars like the sun, of course, live longer and have time to kind of move out and out of their spiral arm kind of thing and continue on their journey around the galaxies. So, you know, those large ones are the ones we kind of look at because they haven't traveled very far from their birthplace in there. So little minor fluctuations in the galaxy disk or gravitational interactions, maybe with passing galaxies, might be able to start a density wave. And so they're starting to hint about merging or interactions with other galaxies can actually have something to do with that spiral arm formation. And there's good evidence on that. So this density wave theory does not account by itself for the branches and the spurs observed in the spiral arms. If that density wave theory was the only thing we were going by, we would have just a two-armed spiral galaxy, perfectly smooth spiral arms, okay? Two spiral arm patterns, if that was the only thing that was causing the spiral arms. But obviously that's not it. We have the little fragments and the spurs happening. So this has prompted the idea of mergers or little hitchhiker kind of galaxies happening. So kind of interacting to form those spurs as well. So yeah, the self-sustaining star formation where the birth of stars, remember the birth of stars can also give you a shock wave. So not only the supernova death of stars, but the birth of very massive stars can also cause a shock wave. So it's almost like a self-sustaining star formation happening where star formation triggers more star formation, so self-sustaining kind of process. So together, self-sustaining star formation plus differential rotation, maybe picking up a few hitchhikers along the way, galaxy interactions can kind of account for the spurs and the fragments. So only the spiral density waves can generate, you know, a two-armed, smooth, grand kind of design of a galaxy. So we've got a few other things kind of happening that give us the spurs and the fragments in there. So the origin and history of the Milky Way. So paleontologists, of course, study and try to reconstruct the history of the Earth from the fossil record in the rocks, right? Well, our old leftover fossil kind of thing is trying to look at the spherical component of the galaxy. If you remember, I mentioned how there's are older stars out there, kind of sparsely populated, not as much gas and dust, so there's not new stars forming there, so it's kind of like the fossil is the spherical component of the galaxy. And the stars in the halo formed when the galaxy was much younger. We can take a look at the chemical composition and the distribution of these stars that can provide some clues on how our galaxy formed. So they try to put together an idea of how the galaxy formed. And so in looking at compositions as well will come into play. Okay. So how old, you know, do they think the different portions of the galaxy are? So the age of the Milky Way galaxy. The oldest kind of open clusters are about 9 billion years old. Now these ages are determined by, of course, we're looking at the stars in a cluster, looking at the HR diagram, and where are they turning off? Where are they evolving off the main sequence? We call that turnoff point, if you remember that from our star unit. So by analyzing their turnoff point of the HR diagram, we can kind of get a rough age for the various parts of our galaxy. And the disk part roughly is about 9 billion years old. So that's the disk part where the spiral arms are. And of course, that's the younger part because the spherical component with the halo and that's older, right? So a little bit older. So we look at the star clusters and see kind of the age for that cluster. In the halo, remember all the globular clusters in there, and so they have some turn-off points in there where that's estimating that it's about 13 billion, on the order of about 13 billion. So really, really old portion is sort of out there in the halo stars, those globular clusters. Remember, those were the older ones. So anywhere from 11 to maybe 13 billion. So averaging about 11 billion, but the oldest are a little bit over 13 billion. So the halo part of our galaxy must have formed at least 13 billion years ago, and so that's much older than the disk portion of our galaxy. So they're kind of putting together and piecing together the formation, how the galaxy ended up forming, and then taking a look at those differences between the stars. And so we've separated them into different populations. Population 1, population 2 stars is what they're called. And so taking a look at population 1 stars. So of course, stars between our two populations fuse the nuclear fuel, ordinarily the hydrogen into helium, right, in nearly identical ways. They're doing that. That's a normal thing that they do. They are differing only in their abundance of what we call metals. And in astronomy, it's not accurate for chemistry, but any atom heavier than helium, astronomers call a metal. In chemistry, we know that's not necessarily true. But so their abundance of metals, so atoms heavier, elements heavier than helium, okay? We refer to those as metals. And so depending on their metal abundance, okay, is one thing. On how we're classifying these as population 1 stars and population 2 stars, okay? So they're doing their normal thing, but what they're made up of does vary. So a population 1 star are what we would call metal rich. They have more abundance of metals, 2 to 3% metal abundance, versus a population 2 star, which is metal poor, we would call that. Okay, so very young, very bright stars. This would be newer kind of population stars. They're younger, right? So population 1 stars are called the disk population. Maybe I'll get some categories going here for us, just to look at those kind of differences. So population 1 stars. So also known as disk stars. Disk population, meaning that these are what we're going to find with these characteristics in the disk of the galaxy. Okay, so metal rich. They're young, right? They're a younger generation, and massive stars. Found in the spiral arms. And so they are in the disk component, and if you remember, the disk component have that nearly circular orbit. So so metal-rich, young stars in the spiral arms, disk component stars that have those circular orbits. So they tend to have these similarities between them. So disk population stars, circular orbits of the plane of the galaxy, young stars. So within the last few billion years, they formed. Our star, the sun, is a population 1 star. So this is a younger generation of stars within the disk region, and they have more metal in them, metal abundance in them. Okay, population 2 stars, sometimes called the halo population. So they're out in that spherical component of the halo, and so population 2 stars. Halo population stars. And definitely these are going to be metal poor. They're old, low mass stars. That are main sequence or globular clusters. Sequence in those globular clusters, remember, those are out in the halo. And these have very elliptical orbits. Remember those? Out in the halo kind of had the swarm of bees, kind of elliptical orbits to them. So quite a bit of difference going on between our different population stars, and that they are in different components of our galaxy. So we can kind of start to put together a theory between our populations of stars. And yeah, this should actually be 12.1. PowerPoint says 9.1, but it's your chapter 12. Stellar populations, population 1 over here, population 2 on this side. So you might want to take a look at that, where as far as what their location is, their metal abundance, the shape of their orbit, and then their average kind of age, and put that kind of all together by looking at the summary here. And so population 1, we got what we call extreme versus intermediate, because you can have variations between your population 1, but basically they're in the disk or the spiral arm region for your population 1. Pretty decent amount of metal abundance. Extreme population 1 stars are 3% metal abundance, and then we've got sort of intermediate here at a 1.6, but again, more metal abundance, okay, in these are younger generation. The shape of the orbit, basically circular, okay? And so they're young, 0.2 billion and younger. In this group, 0.2 to about 9 or 10 billion. So that disk region, younger region. So why is there more metal in this younger population? So this element building cycle. So older generations, so your population 2 ones, in the beginning kind of the universe, we had the hydrogen and the helium from the Big Bang, which we'll have more to say about the Big Bang later. But those were built up, it was mostly hydrogen, mostly helium in the universe, and so those don't have a whole lot of metals, okay, in them. But as we learned that the metals are cooked up in the stars, so those very massive stars, as they are going through their life cycle, they're building up elements greater than helium, right? Fusing hydrogen to helium in their cores, and then they get the inert helium core, and that gets hot enough, and we get the carbon and the oxygen all the way up to iron, right? And so then, during their death, the supernova explosions, those are going to build up even heavier atoms of our metals, our rare kind of metals, and spew all that out in the dust and the gas. And then younger generations come along and they're built up by the interstellar medium that has been enriched with metals, okay? So that's why our younger population 1 stars have more metal abundance, okay? So population 2, either in the central bulge or the halo, so the spherical component, and we've got very little percentage of metals in these elliptical, either moderately or highly elliptical orbits out there in the halo, right, swarming like these. And then their ages are greater. So we got 10 billion to 13 billion years old. So population 2 stars are out there in the spherical component, the halo or the central bulge. They're older, don't have very much metal abundance, very elliptical orbits, versus population 1 out in the disk, a much younger generation, more metals, and circular orbits. So make sure you've got a distinction. It's a bullet on your study guide. Make sure you've got a nice distinction between your stellar populations with all those variables in there. Okay, so the atoms of which we are made of were created in the process of these span of generations of stars. And so as generations would go by with the stars, you would increase the metal abundance, right? Because the new stars had more metal in them, they built up more metals, died, and then the younger generations as you go definitely would have more metal abundance as that history would build. And so yes, led to sort of the Earth being formed and life on Earth. So we being created in the Milky Way galaxy, or we are stardust, has a truth to it, a true ring there to us. And so we've learned about how those massive stars, you know, make it to iron. They're shorter lived kind of thing. Why we're getting the carbon and nitrogen and oxygen being so common. And then the rarer gold, silver, platinum, uranium, these things are rare and often valuable because those are much heavier elements that really took some massive stars to die in supernova explosions to build up that. Okay, and this is just showing chemical abundance of the elements. Here, kind of looking at it in an exponential kind of a scale, mostly hydrogen, some helium, and then what we're seeing in our stars, carbon, nitrogen, oxygen, iron. We got a little calcium along the way there. So iron's kind of like the last road for our star. And then of course you would have more during a supernova explosion. Here's looking at that same chart, but in a linear fashion. So hydrogen here, helium, a little blip here for carbon, nitrogen, and oxygen, a little blip there for iron, if you remember that. When the galaxy kind of first formed, you know, you had very little. You had mostly hydrogen and helium. And so what their idea here is the stars had not manufactured much metals yet. So that's why these earlier, really old generations of population 2 stars don't have very much metal in them. It took several generations before our younger population 1 stars could have enough of that metal abundance. And so they're just sort of talking about the element building cycle here. Okay. Each generation adding more and more metal abundance. So, yeah. The oxygen atoms we breathe, the carbon atoms in our flesh, the calcium in our bones were all created in the interiors of those, you know, very massive red and yellow giants, right? And they were hot enough to sustain the fusion reactions beyond the helium, right? Took very massive stars for that. The gold and silver and our jewelry and our dental work and such created in the supernova explosions. Those conditions are hot enough to finally fuse higher than iron, if you remember that. So, very significant idea to take away from an introductory astronomy course is that you and everything on Earth are made of stardust, right? So, all of those elements cooked up in the stars. So, kind of fun to think about. Children of the Milky Way. All right, so trying to put together a model then by studying our different populations of stars. In the 1950s, we began to develop a hypothesis called the monolithic collapse model. So this is kind of earlier model. But in science, if observations aren't always matching what our hypothesis is, sometimes we do have to tweak that a little bit, and that is what they had to kind of evaluate this. But the premise of it is, here we have our first stars being metal poor, because no other stars had existed, right, earlier to put that in the gas and dust to create that. But here we have a contraction of a large turbulent gas cloud that would produce the spherical component of the galaxy. It's the first star, sort of this blob here, coming together. In the second stage, that's going to kind of be the spherical component. The second stage here is allowing this rotation to happen of that low density cloud. Kind of can't remain spherical like that. It begins to flatten out because of the rotation. I think they liken it to a blob of pizza dough. As you continue to rotate that, it will flatten out into a disk. And so that spherical, because that high internal pressure balances its gravity, okay, and then it begins to flatten out into a disk. Okay, of course, over billions of years that it takes for this to happen, but it's starting to flatten out. Now, notice how stars and the globular clusters that had first formed out there in the halo, the spherical component, okay, aren't getting affected by it. They're actually staying in their general vicinity where they were born, and so they kind of get left behind, and then our cloud is beginning to flatten as we continue to rotate. And during then that flatter kind of region, later generations of stars are starting to form, okay, along the disk kind of region in there. And these stars would have more metal abundance because those earlier generation stars had cooked up, you know, more metals and spewed it out. So the gas and cloud dust that these were newer stars were getting formed in the disk region had more metal abundance, and so they're flattening out. So then we've got those stars that are in the disk that are metal rich, and they're following that very nearly circular pattern, okay, in the disk region. So that monolithic collapse kind of theory is one way that they do describe how the galaxy began to form. Okay, and this does clear up a lot of little questions and accounts for many of the properties of the Milky Way, but you know, they've got a little bit of an improvement on that. What that older model, the monolithic collapse theory, couldn't explain was why those globular clusters, those older globular clusters, weren't metal free. Why that oldest generation of stars weren't metal free. Okay, that would make sense. Why wouldn't they be metal free? No earlier generation of stars had lived. You know, why would we even see any metal in them? So this prompted kind of in the 1980s to think about this. Not all globular clusters seem to have the same age. They weren't all metal free. And the younger clusters seem to be kind of even in the outer halo. So what was going on? Why did we have sort of some discrepancies that our model wasn't quite explaining? So yeah, and the oldest stars weren't metal, I mean, they were metal poor, but they weren't metal free like we would think they would be. So must have been at least a few massive stars to create those metals for, you know, the generations of those to have at least some metal out here out in the halo. So what, you know, what was going on with that? So they think they've got it kind of figured out where the hitchhikers, the mergers of other galaxies. So sort of some of those metals in the oldest ones surviving today, could it be explained that uh, these hitchhikers, they call them, maybe belong to other galaxies, and we're kind of merging as our Milky Way galaxy, which is a very large galaxy, might have kind of snapped up some of these smaller kind of hitchhikers along the way. So some of those globular clusters could have been captured by our galaxy. So this idea of some galaxy mergers happening could explain the range in globular cluster ages and a little bit in their compositions. And so in science, yeah, they do have to modify some of their models if it's not matching observations. Okay, so that's kind of this idea of mergers that have happened to help us explain what's happening. So the fact that these population 2 stars weren't metal free out there in the halo, that mergers with other galaxies and the infalling gas from that could contribute to the disk. Okay, let's see. And the metal abundance and the ages of the stars in the galaxy do seem to be very important clues. Metal abundance and the age, it doesn't tell the whole story, but it does give us a good idea on a model to try to mimic how these things were forming. So that's the basic kind of formation of our galaxy, how they think it began to form and why we're seeing, you know, the different populations of stars. But now we want to take a look at the nucleus of the galaxy. The most mysterious region is the center of the galaxy, what we call the nucleus of the galaxy. And so it's not a lot that we can see out there right at the center. So visual wavelength observations reveal nothing about the nucleus because there's so much gas and dust in the way. So we try to observe it at longer wavelengths, as we mentioned, the infrared and even the radio wavelengths of the electromagnetic spectrum. We have good success in taking a look at that. But if you remember, Harlow Shapley's study of our globular clusters placed the center of our galaxy in the direction of Sagittarius, the constellation of Sagittarius on the sky in that direction. Okay, Harlow Shapley helped us with that. The first infrared map, okay, of the nuclear bulge was Eric Becklin in 1968, and it showed a location, and he did this in radio waves, okay, showed where the stars are most crowded together, kind of identifying a gravitational center of the galaxy, and they did find it in that direction of Sagittarius, the constellation. So it did back up what Harlow Shapley was thinking. So the higher resolution radio really did show complex kind of concentration, a collection of radio sources. They call that one collection the Sagittarius A star. So Sagittarius in the direction of that constellation on the sky, and Sagittarius A with a little star symbol. So they do abbreviate that Sag A star. Okay, with that, Sag A star. Very few astronomical units in diameter, but a very powerful source of radio waves coming from that region. Tremendous amount. Infrared radiation, radio waves coming from there. And it appears to be crowded stars and dust warmed by those stars, just really some sort of activity happening right in and around those. So what could be so small and create such a large amount of radio wave energies in that region? So it gets them to kind of speculate here about that center of the galaxy, the Sag A star, and looking at sort of complex structures very near Sag A star by magnetic fields and rapid star formation in that region. Supernova remnants are showing that the massive stars have formed there recently and died explosively, right? So we're getting some youth going on in there. And yeah, this is in the infrared wavelengths, kind of brightens that up so we can see through all the dust in that region. The center is very crowded with stars, a tremendously dense kind of region in there, heating up the dust and producing really strong kind of infrared wavelengths, so very warm region. And there is evidence that Sagittarius star, so the center of the galaxy, something that's very massive but yet small. If you remember our talk about very compact objects with star deaths, it is believed that there is a supermassive black hole at the center of the Milky Way galaxy. So this would not be just a single stellar or a star death. We talked about our star deaths, but this is something that was created as the universe was created. So this primordial kind of black hole. So a supermassive black hole into which some gas is flowing. So a region that's really compact with a lot of stars and activity going right around this. So we can't really see the center of it, but we can see a lot of activity and the motion of the stars around that concentrated center, and their orbital speeds are very rapid, so there is something very massive right there. And so yeah, they do believe that the center of the galaxy, Milky Way galaxy, contains a supermassive black hole, and for that matter they think that most galaxies do have a supermassive black hole. So you know, evidence is leading them that it does seem adequate that the galaxy nucleus does contain that supermassive black hole for those various reasons. A very concentrated radio observation at the center of the gas clouds, the motion of those stars, very rapid. Yeah, so crowded with stars, this does indicate very massive object. You know, there's not a lot of energy coming out of it, and so it does make it quite interesting that their thoughts are that there's a supermassive black hole. And they also think that our Milky Way galaxy might kind of be on a starvation diet, or every now and then only gets a trickle of maybe a star kind of following into the black hole and being ripped apart by the tides, yeah. But it may be mostly dormant and lacks a fully developed accretion disk around it because that rate of matter flow is pretty low at the present time. But as we do look at other galaxies, we're going to find some that are incredibly active galactic nuclei where there is some definite infalling of gas and dust creating activity in those around their black holes. So supermassive black holes at the center of the Milky Way galaxy. Okay, so not the remains of just a single dead star, but it contains way too much mass. It probably formed when the galaxy first formed. So these sort of primordial supermassive black holes are their thoughts on that over 13 billion years ago. So I think that does conclude, yes, that does conclude our chapter 13. I'm sorry, chapter 12. We're not quite to 13 yet. That will be next time. So do make sure that you go through your little study guide and look at each bullet and make sure you have some good information on each of those. And as always, if you have any questions, just get with me.